Today we're going to be talking about ideal gas law. Now when I talk about ideal gases, these aren't things that exist in the real world, but they're how gases would behave if everything was ideal, if everything was perfect and imaginary. Now, my chemistry teacher used to say that ideal gases are like ideal men and they don't exist. I don't want to be that bitter, but for now, know that ideal gas laws behave a little differently than they do in the real world. But the acronym that you want to remember for today is PIVNERT. If you can just keep saying PIVNERT, 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 you'll remember what the ideal gas law stands for. So we know that P stands for pressure, V stands for volume in liters. It's very important you're always using liters as your unit. The small n is for number of moles. R is the gas constant, I'll talk about that in a minute. And T is temperature in Kelvin. Remember that you always must use Kelvin to calculate ideal gas law. Now when we say gas constant, these are numbers that you're going to be using, that they're constant. We always use the same numbers. You don't have to memorize these. I got this little piece of information from your star chart, so you'll always be able to look these numbers up. Now depending on the units, we're going to use a different gas constant. If the pressure is given in atmospheres, so again, if you're given the pressure in atmospheres, the gas constant is going to be 0.0821. If you're given the pressure in kilopascals, the gas constant is going to be 8.31. And if you're given the pressure in millimeters of mercury, the gas constant is going to be 62.4. Again, you don't have to memorize these. They'll always be in your star chart. So as long as you know how to use them, then you'll be good. So let's look at a sample problem. We have a 5.60 liter sample of an ideal gas. It contains 0.954 moles, and the pressure is 742 millimeters of mercury. We want to find the temperature. So we know we've got our volume 1, our liters. We've got N1, our number of moles. And we have P1, our pressure. So, PIVNERT. We want to just plug in the numbers that we need for PIVNERT. Pressure is going to be, P is going to be 742. Volume is 5.60. Note that it's in liters. N is 0.954 moles. And our gas constant, remember that here we're given pressure in millimeters of mercury. So we want to find the gas constant for millimeters of mercury, which in this case is going to be 62.4. Since we're using millimeters of mercury, that means the R is going to be equal to 62.4. So we're going to plug that in. And what we're going to solve for is we're solving for T. So now it's just a simple step of solving for T, solving for a variable. Multiply 742 times 5.60 and we get 4155.2 is equal to multiply 0.954 times 62.4 and we get 59.53 times T. So now to solve for T, we're going to divide both sides by 59.53 and we end up with T is equal to 69.8 Kelvin. Remember that temperature is always given in Kelvin. So this is a very straightforward ideal gas problem. All of the variables were given to us, and all we needed to do was solve for T. The next one is going to get a little bit more complicated. Here, we know that we have 19.6 grams of methane. We have the temperature is 27 degrees Celsius, and the pressure is 1.59 atmospheres. So our first thing is we're given the mass. What we need to find is the number of moles. Remember, PIVNERT only works if we know the number of moles. We have our temperature in Celsius, not good enough. We need to convert to Kelvin. And we have our pressure. So, to convert our temperature to Kelvin, we add 273. 27 plus 273 is equal to 300 Kelvin. So now our temperature is going to be 300 Kelvin. We've got PIVNERT, remembering this acronym the whole time. And the most important thing is even though we're given the mass, we can use this to find the number of moles. So our next step is to convert 19.6 grams of methane into moles. So to set this up, we start off with 19.6 grams of methane. We want to set up our dimensional analysis. Remember, if we've got grams on top, we're going to put grams of methane on the bottom, converting from grams of methane to moles of methane. And whenever we want to go from grams to moles, we're going to use the molar mass. So 1 mole of methane is equal to 1 carbon plus 4 hydrogens. So the molar mass of carbon is going to be 16.05 grams. That's 1 carbon plus 4 hydrogens. Multiply everything on top, divide by everything on the bottom, and we end up with 1.22 moles of CH4, of methane. So this is going to be N. This is our number of moles. So setting up PivNert, we have pressure is 1.59. We're solving for volume, we don't know that yet, is equal to 1.22 moles, that's N. The gas constant here, remember we're given our pressure in atmospheres. We want to look up atmospheres. If the pressure is given in atmospheres, that means our gas constant is going to be 0.0821. So we're going to plug this number in for R. And last but not least, we're solving for, we need to find temperature. Temperature is 300 Kelvin. So now we have all of our variables plugged in. All that's left is to solve for volume. Multiply everything on this side, and we end up with 1.59 volume is equal to 30.05. That's 1.22 times 0.8 times 0.08 times 300. Divide both sides by 1.59, and we end up with volume is equal to 18.9 liters. So that's our answer. Now the last problem is going to be the trickiest one that we'll see. This one we need to use stoichiometry. Now notice that we're just given a description of the reaction. We have 3 grams of potassium chlorate decomposes to form potassium chloride and oxygen. Now here we know the oxygen gas has a temperature of 24.0 Celsius and a pressure of 0.948 atmospheres. And we're solving for the volume of oxygen gas. Keep in mind, we want to find the number of moles of oxygen, but we're given grams of potassium. What we need to do is we need to convert from grams of potassium chlorate to moles of oxygen, and this means we need to go back to do stoichiometry. So first, we know our mass, our temperature, convert our temperature to Kelvin, and now it's 297 Kelvin, and our pressure is in atmospheres. So writing out our equation, potassium chlorate, remember we've got potassium and chlorate, decomposes to form potassium chloride, KCl, and oxygen. It's one of our Brinkelhoff elements, so it's going to be O2. Now notice how this equation isn't balanced. So our next step is to balance the equation. You can pause this, try this on your own. But when we balance the equation, we're going to end up with 2 KClO3 plus 2 KCl is going to give us 3 oxygens. So now we've got a balanced equation. Now we can set up our stoichiometry ratio. We want to convert from grams of potassium chlorate to moles of oxygen. So our first step is to go from grams of potassium chlorate to moles of potassium chlorate. So we want to set it up so that 1 mole of potassium chlorate is equal to 122 grams of potassium chlorate, adding up 1 potassium, 1 chlorine, 3 oxygens. Now we've got moles of KClO3. Our next step is to go from moles to moles. So again, going from moles of potassium chlorate to moles of oxygen. Here's where we use our coefficients. For every 2 moles of potassium chlorate, there's going to be 3 moles of oxygen. So we've got 3 up here, 2 down here. Notice that our units match up. If we've got grams of KClO3 up here, we've got grams of KClO3 down here. Moles of KClO3 up here, moles of KClO3 down here. So last step is to multiply everything on top, divide by everything on the bottom, and we end up with 0.0367 moles of oxygen. That's converting from grams of potassium chlorate to moles of oxygen. So now we know our number of moles, and we're ready to plug this into our ideal gas equation. So we've got PivNert as the acronym of the day. We know our pressure. We're solving for volume. We don't know that yet. We know a number of moles, we know the gas constant, and we know our temperature. Pressure is 0.948 atmospheres. Volume is we're solving for that. Number of moles is 0.0367. Our gas constant, here, we're given our pressure in atmospheres. So we want to look at atmospheres. The gas constant is going to be 0.0821. And temperature, after we've converted to Kelvin, it's going to be 297 Kelvin. That's 24 plus 273. So now all that's left is to solve for V. Multiply everything on this side together, and we get 0.948 times the volume is equal to 0.895. Divide both sides by 0.948, and we end up with volume is equal to 0.944 liters.